All right, welcome back. We're continuing our discussion of related rates exercises. So we're going to amp up the difficulty just a little bit. Not too bad, but this will take a little more work. Let's see what it is. Let's hop right in here. Let's consider a coffee mug with a diameter of 4 inches and a height of 3 inches. A pour over. Ooh, that's kind of a funny typo. Canonical. No, canonical. That refers to that refers to like things that are canon. Like I think it came from like that word originated with the Catholic Church, the canon being the holy works or whatever. Um, but now people refer to canon like the canon of Star Wars. It'd be like the stuff that's real Star Wars or the canon of Marvel Universe or whatever. So the word I was actually looking for is conical. That's kind of funny though. I'll fix it before you ever see it. So conical coffee maker. Yeah, we're going to fix that right there. Conical instead of canonical has the same dimensions. So I don't know if you've seen these before, if you're a coffee drinker or not, but they have these, they're called pour-over coffee makers. Basically, it's like a cone, and then it has like a little stand that attaches to your top of your coffee mug like that, and then you can make a single cup of coffee. It's instead of having like the big pot of coffee where it takes 10 minutes or whatever, and then you have a ton of coffee. This brews basically a cup of coffee, one mug at a time, and so they're convenient in that sense. Okay, so that's the situation we have. If the coffee is draining from the coffee maker into the mug at a rate of 10 cubic inches per minute, determine the rate of change in the height of the coffee in the filter when the height of the coffee is in the filter is 3 inches deep. Oh, yeah, so that's question one. So let's maybe put like a 1 right there. I think this is a two-parter. Then question 2 is determine the rate of change of the height of the coffee in the mug when the coffee filter is 3 inches deep. Okay, so let's take part 1 first. So we're concerned about the rate of change of the height of the coffee in the cone. Now, what are we working with? Okay, a cone. So that's pretty obvious. We're talking about the height of a cone changing. What else are we talking about? Well, coffee is draining, so what's being affected here? If coffee is draining at the rate of 10 cubic inches per minute, like we're told, what feature of the cone is changing? Well, its volume is changing. So we could say, by that second or third sentence, that the rate of change of the volume of the cone is 10 cubic inches per minute. Specifically, so we can say, given what we know is that the rate of change of the volume of the cone, so we'll say, dV dt, the rate of change of volume. Now, careful, in the sentence it says 10, but let's think about this. The volume of the cone, the volume of the coffee is getting smaller. When a quantity is getting smaller, it's going to have a negative rate like so. So negative 10. We got to be careful with that respect. The amount, the quantity is getting smaller, negative rates, decreasing. Okay, if it was increasing, it would be a positive rate. But you got to be careful with how the sentences are worded and versus translating that into mathematical symbols. Okay, has to be negative here. Now, what do we want? We want the rate of change of the height of the coffee in the filter when the coffee in the filter is 3 inches deep. So when H is 3, the height is 3, we'll call it H. Now this is like the little cone of coffee. We want to find dH dt. So let me do this real fast. Find or need dH dt. dH dt. Okay, so what about our formulas? Okay, so this might be one that's stored in the back of your brain somewhere, but I know you've seen this before. If you've been through high school and middle school math, you've seen the volume of a cone before. The volume of a cone is V, it's 1/3 times the volume of the corresponding cylinder. So times pi r squared h. You basically take the 1/3 times the area of, like, you can think the top of the cone times the height. Okay. Now, okay, so here's the problem right away though, is that cone, volume of the cone equation, that has a V in it, which we want, because we know what dV dt is, so we like the V. 1/3 pi, that's fine. It has an r squared and an h. Now, we are going to solve for h dh dt eventually, so we want the h there, but we don't really care about the radius. Like, nowhere in the question are we being asked about find the rate of change of the radius. Now, I guess we could write a question that concerns the radius, but this particular question does not care about the radius. So the thing is, we need to rewrite this volume equation such that it only has what we are concerned with, which is V's, good, constants are fine, and then H's. In other words, I need to figure out a relationship between R and H so I can substitute and rewrite my volume equation in terms of H. Now, here's a tool to put in your related rates calculus toolbox. Similar triangles. Now, similar triangles, I know you've had geometry probably at some point. It might have been a few years. But similar triangles basically occur, and they have some nice properties. And the similar triangles that I'm referring to here are in this cone. If I draw a vertical line, right here, into like the center of the cone, over here, so there's one triangle. That's like the big triangle. Imagine that would be like a half of a cross section of the cone if the coffee filter was all the way full. Now, I also want to do the same thing except for like the actual coffee level. So that would give me another triangle like right this, like this. So basically I have two triangles. I'll call it the big triangle like this, and it's half of a cross section of the entire cone. And then I have a smaller triangle like this. That's half of the cross section of like just the cone that's made by the coffee, the liquid. Okay? Now, if you see here, they share this angle right here. They share that angle. And they're also both right triangles. What does that mean? That means they are similar because all of their angles are equal. Basically, if you know two of the three angles are congruent, the third angle has to be automatically congruent in Euclidean geometry. And that means they're similar. Now, similar triangles have some very nice properties. Specifically for us, their sides hold the same proportion. Now, how does that help us? That helps us because we know the dimensions of that big triangle. Because the dimensions of the coffee filter are the same as the dimensions of the coffee mug, which has a height of 3 inches. So height of 3, and has a diameter of 4, which means radius of 2, because radius is half the diameter. Okay, but now radius and the height, R and H, that's what when we write this cone right here, the volume here, we're talking about the volume of the coffee, the liquid here. And so R and H are the height and radius of the cone that describes the coffee area. So the coffee, the R and H, they label the height and the radius of the small triangle. And here's where the similar triangle business comes into play. The proportion of, let's say, the height of the big triangle to the height of the small triangle. And if you take the proportion of that other leg of the large triangle to the other leg of the small triangle, they have to be the same proportion. That's just a known geometrical fact. How does that help us? Well, from this equation, we can now either solve for H or solve for R. Cross multiply, clear the denominators, and we get 3 times R equals 3 times R equals 2 times H. Now, here's the question. Do we want to solve for R or do we want to solve for h? Remember, I think I mentioned this a few minutes ago. We want an equation that relates the volume and height, not r, not radius. So if we solve this for r and say r equals 2h over 3, we can now go over here and plug in for r 2h over 3 squared times h, and now we have a volume equation in terms of h only. Of course, I need to clean it up a little bit, but it only has v's, h's, and constants, which are fine. All right, so let's clean that up a little bit. V equals 1/3 pi. 2h squared would be 4h squared over 3 squared would be 9 times h. Clean it up a little further. We get 1. Actually, let's combine all of our constants, all of our scalars. We have 4 pi on the top. And on the denominator, 3 times 9 is 27 times h cubed. If I could ever write a 3 good, that'd be nice. I have the hardest time with 3s like this. Okay, 4 pi over 27 times h cubed. Now I have my volume equation in terms of h. Nice. So now I'm to the point where I can find my implicit derivative with respect to time. So I differentiate with respect to time, plug in my known, solve for my unknown, and we should be able to get dh dt. Remember, that's our goal. We need dh dt, which should be here in short order. Okay, so let's go from here. Now let's differentiate. So we're going to take the derivative with respect to t of the left-hand side equals the derivative with respect to t of the right-hand side. Of course, the derivative of v, it's like a v to the first power with respect to time, is just dv dt. Nothing crazy there. Now notice I have a constant multiple on the right-hand side. So I can factor out a 4 pi over 27 times the derivative with respect to t of the variable portion h cubed. Okay, and again, my 3s. So let's see here. The h cubed, like so. Okay, there we go. All right, and so now we can finally get our related rates equation. dv dt equals 4 pi over 27 times 3h squared. Now again, it's not just 3h squared because we just took the derivative with respect to time, so it's 3h squared times the derivative of h with respect to t according to the chain rule. So here is our related rates equation. And now we can plug in our knowns and solve for our unknowns. What do we know? We know h equals 3 because we're considering the exact moment when the height of the coffee is 3. And we know that the coffee is draining at 10 cubic inches per minute. So dv dt is negative 10. So I plug in negative 10 for dv dt. And we have 4 pi over 27 times 3 times what h is 3 squared times dh dt. Now notice the only quantity that's unknown is the one we're after, dh dt. And so it's just a matter of now dividing appropriately to solve for dh dt. So dh dt is what? Okay, well, it's negative 10. Let's see here. So we're going to have negative 10. Let me grab a calculator. We're going to divide, okay, dividing by 4 pi over 27 is like multiplying by the reciprocal. So that would be negative 10 times 27 divided by 4 pi. I'm not going to divide by the 4 because I don't want to approximate the answer. I'm just going to put so there's supposed to be a pi on the bottom basically here, and I want to leave that alone. So we're going to divide by 4. Then we're also going to divide by what? 3 times 3 squared, so divide by 27 as well, and we get negative 5/2, and then there's that pi on the bottom. So what are my units? We're talking about inches. Okay, so the height is a linear measurement, so inches, and we're talking about minutes, so inches per minute. Okay? So that's the rate of change of the height of the coffee in the filter. That's question 1. Okay, not too bad. Where were we at? 15 minutes, not too bad. Now question 2. Question 2 actually turns out to be a little easier. We did the hard one first. The question 2 is easier as long as you recognize one special feature about a cylinder. So determine the rate of change of the height of the coffee in the mug when the coffee in the filter is 3 inches deep. Now here's what you got to realize. All we really care about is that the coffee is draining at a constant rate of 10 inches per minute into the mug. So it doesn't really matter that the coffee in the filter is 3 inches deep, because we're concerned about the mug, and we know that the mug is being filled at a rate of 10 cubic inches per minute. So let's think about this mug, okay? Well, what do we know about the mug? Well, we're told in the first sentence that the height is what? 3 inches. And the radius, okay, the diameter is 4, which means we're probably going to need the radius instead. Then the radius, that would be 2 if the diameter is 4. Okay. Now, we're talking about what? Okay, so coffee is draining from the filter into the coffee mug and making the level in the coffee mug rise. So determine the rate of change of the height in the coffee mug when the coffee filter is 3 inches deep. So we're talking about, you know, the coffee level in the mug rising. Now, what's that shape going to be? Well, it's a cylinder. So let's go over here and say, okay, volume of cylinder. Cylinder. I need to work on my spelling a little bit. Cylinder. Okay. Well, what's the volume of a cylinder? That's going to be V equals, okay, very similar to the cone, except no dividing by 3. Pi r squared h. Area of the base times the height. In fact, anytime you have a regular geometric solid, that is like a solid that has the same cross section for its entire, I guess, height, if you want to think about it that way, it's always the area of the base times the height. And a cylinder fits that description. Okay. So here's the curious thing. The curious thing is this. The radius of that cylinder does not change. And I've kind of mentioned this offhand a few times, that we can substitute into our formula immediately if we know the quantity we're substituting in does not change. Here, the radius of the level in the coffee mug does not change. Because the coffee mug has a constant width, the cylinder has a constant width the entire way up. So you can think about this 2 ways. I suppose you could differentiate, and you would get a related rates equation in 2 variables, which one of those would be a dr dt. And you would ask yourself, what's the rate of change of the radius? And if you thought about it long enough, you might think, oh, the radius isn't changing, so it has to be 0. And then that would simplify your equation and you get the answer. Or, at the onset, just think to yourself, the radius isn't changing. So I can go ahead and say r is 2 and plug it in. Now, I could not do that on part A. Why could I not do that? Because think about up here in the cone, up here, that cone shape is changing when the coffee level drains. and as that cone shrinks, the radius changes. Now, that's why we could not do this up above and plug in a radius to start with, because the radius was changing. But with the cylinder, it has a constant radius, so you can go ahead and substitute the known value for r. And so we can say that v equals pi r squared, so 2 squared h, or v equals 4 pi h. And now we have our related rates. Sorry, not there yet. We haven't differentiated. We have our equation that relates v and h because we want to know the rate of change of the height of the coffee in the mug. So now we differentiate and we get derivative of the left-hand side, v, equals derivative of the right-hand side. That's what, 4 pi h. Of course, just like before, we get dv dt on the left. Now let's cut to the chase here. We know we have a 4 pi, that's a constant multiple. So you get 4 pi, technically we're factoring out the 4 pi, then differentiating the h. So we have an h, think about h to the first power. The derivative of h to the first power, it's a h with respect to t. So we take the derivative of h, the outside function, we get 1. Evaluate the inside function, but that's a constant one, so we can't evaluate it and do anything, change it. You just get 1. But then you have to multiply by the derivative of the inside function, so you have to multiply by the derivative of h with respect to t, and so you get 4 pi times dh dt. Okay, now we plug in what we know and solve for what we don't know. I guess I didn't actually address this. I probably should have. What do we want? We want the rate of change of height. So, this is for part B. We need dh dt, just like before, the rate of change of the height. But what are we given? Now this is, you gotta be careful here. We're given that dv dt equals what? The rate of change, the volume of the coffee in the mug. Okay, the rate of change of the volume is 10, we're told. Is it positive or negative? Think to yourself, is the coffee, the volume of the coffee in the mug, is it expanding or is it contracting? It's getting bigger, right? So it's a positive 10 this time. Whereas before, the cone was draining, and so it was a negative 10. Here, the coffee is level, the coffee volume is rising, so it's a positive 10. So here's our related rates equation, and we can just plug in. We know that dv dt is 10 equals 4 pi times dh dt, and now we can easily solve this for dh dt. Divide both sides by 4 pi, and we get dh dt, okay, what, 10 over 4 is 5 over 2? So 5 over 2 pi. 5 over 2 pi. Interesting. 5 over 2 pi negative, 5 over 2 pi positive. Coincidence? Think about it. All right. We will do another couple examples in the next video. Again, if you want tons of examples, I have tons of examples on YouTube of related rates examples, lots of different ones, and you can watch YouTube, other folks do related rates examples to your heart's content, but practicing is what it takes here. I know these are hard to wrap your head around at first. It took me, the first time I took calculus, or the only time I took calculus, it took me a lot of time to wrap my head around it. And so, practice and watching videos and asking questions, that's the key to success here. Okay? All right, I'll catch you in the next video. Let me know if you have any questions.